All right, so grams per mole is molar mass. We're going to use the grams given from the problem, which was 0.207 grams. It's right here. Okay. And then we just are going to use the ideal gas law to find moles. Again, there are two ways to do this. So let's go back. So if I want to rearrange to solve for moles, I do PV divided by RT, right? This is basic algebra where you move the RT over to the other side. That will leave us with moles by itself. Okay, so now I just plug all of the numbers in. So what was the pressure given? The pressure given was 0.980 atmospheres. Pressure. Okay. The volume given is a little bit problematic because it's in milliliters and it has to be in liters because the R constant is in liters. So 72.5 milliliters, and then there are 1,000 milliliters in a liter. So you would take this number and you divide by 1,000. That's how you turn milliliters into liters. So 72.5 divided by 1,000 is 0.0725 liters. And then I gave you the R constant, so you can just plug that in there. 0.0821 liter atmosphere over mole Kelvin. And the temperature in Kelvin. So I didn't give it to you in Kelvin, I gave it to you in Celsius. So to turn a number to Kelvin, you take the degrees Celsius and you add 273. So 68 plus 273 is 341. Kelvin. So let's look at the units. Atmospheres cancel, liter cancel, Kelvin cancel, and we're left with moles, which that's what we were trying to find. That's what like this missing piece of the molar mass was. So calculate this number. Now the best way to do this in your calculator without messing up is you do 0.980, you multiply by 0.0725, you hit your divide button, 0.0821, and then hit the divide button again. It kind of helps of you avoiding having to use parentheses in the bottom, but it's up to you. So the moles come out to be 0.0025378 something something something. The reason why I write out a bunch of numbers right now is because I'm not finished. You don't want to round your number until the very end. So this number goes in right here. So I take 0.207 and I divide by my moles. And you get 81.6 grams per mole.
I I rounded it up because I didn't have enough space. 81.5.
That's not a big deal. You'll get it right. That's fine. That's 100% acceptable. Okay, this is one way to do this problem. So I guess, all right, so the other way to do it, if you do not like doing it that first way, is to take your ideal gas law and take this where moles equals mass over molar mass. And because I'm solving for molar mass, if I replace the moles with this guy, I can just plug and chug all the way into Perfner. So PV equals now, I have mass over molar mass instead of moles. And then I need to solve for molar mass. That's what the problem is asking. That's the big M. So you multiply both sides by big M because right now it's in the bottom and you can't leave it in the bottom. That will cancel it out over here, right? Now to get molar mass by itself, that's this guy, I would divide both sides by PV. That looks like an R. PV. So divide by PV. That gets rid of the PV over here. And now you just plug all of your numbers in. Okay, so mass was 0.2, shoot, I forgot it, 0.207. The R was given 0.0821 liter atmosphere over mole Kelvin. The temperature was, what was it? 341 Kelvin?
Yes.
Okay. And the pressure was 0.980 atmospheres. And the volume was in milliliters, so we had to change it to liters, 0.0725. So then the atmospheres cancel, the Kelvin cancel, the liter cancel, and you get grams divided by moles, which is molar mass. So this is the other way to do it. It's the same, you should get the same number. The number isn't going to change very much. 81.5, 81.6 grams per mole. So this way, I'm going to guess is going to be easier for you to do it similarly to how we did it the first way for the last problem. So they ask for density. So we need to say, okay, well, what does density mean? Density means mass divided by volume. That's what density is. So kind of like molar mass is grams per mole. Well, grams is mass, right? So if you have mass and you can find volume, you can take the mass and divide by volume. I gave you mass in the problem. The mass of the gas is 1.50 grams. So density is, I have the mass, and it's just like, oh, I just need to get the volume, and then I could find density. So let's look at the problem and see if we have enough information to get us volume. So I have pressure, I have temperature, and I have mass. So let's see. PV equals nRT. If I were to isolate volume, I would be dividing both sides by pressure, right, to get volume. That's kind of what's missing down here. Okay. So you go, okay, I would need R, which is given. Do I have temperature? Yes. Do I have pressure? Yes. Now, in the problem, I didn't give you moles, but I gave you grams, and I told you what the gas was, so I can turn grams into moles. So if you do 1.50 grams of chlorine gas, and you go on the periodic table, and chlorine is 35.45 grams per mole. So that's 70.9, because there's two of them, right? Grams per mole. Now I do have moles, right? So I can plug and chug. So the moles is 1.5 divided by 70.9. The moles comes out to be 0.0211 something, 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 something. The R constant is, let's see. I gave it, we had millimeters of mercury, which is the same thing as torr, so I gave you that R constant. Oops, 62.4. So nRT, temperature was 25 Celsius. So you add 273 to that and you get 298 Kelvin. So nRT divided by pressure. Pressure was 735 millimeters of mercury, which is the same thing as torr. I'll just call it torr instead so it doesn't confuse you. Torr and millimeters of mercury are the same unit. Okay? So look at torrs cancel, moles cancel, Kelvin cancel, and you're left with liters, which is a unit for volume. So you take these numbers, calculate them out, and the volume I got is 0.535 something 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 liters. I just keep the whole number in my calculator. So
I had to like also make that smaller in order to fit that.
okay, so you just try to keep the whole number in your calculator though, even if you write it out smaller. So you take your grams, you divide by your liters. I don't know what, let me look at the sig figs. Sig fig should be 3. So 2.80 liters is your volume. Mass over volume. So basically, this problem is just you trying to find volume because mass was given. You're just trying to use the ideal gas law to find volume. So again, the units were grams per liter, not liters. That was my bad. Okay. Number 3. How many liters, so that would be volume, of ammonia can be produced? I give you a temperature and a pressure, okay? And then I give you 20 moles of nitrogen are consumed. So I give you one substance and I'm asking about another substance. You have to do stoichiometry in this case. There's no way around it. So what is stoichiometry? Stoichiometry is mole to mole ratios. The nice thing about this one is I started you off in moles of nitrogen. So I can instantly jump from moles of nitrogen to moles of ammonia because that's who I'm asking for because I'm already in moles. So let's go here. 20 moles of nitrogen. And I will do my stoichiometry now. I will jump from my moles of nitrogen to my moles of ammonia using mole to mole ratios. You have your balanced reaction down here. I balanced it for you. So for every 1 mole of nitrogen that react, 2 moles of ammonia are produced.
I got 40 from that.
Okay, I'm going to keep going though. So this is 40 moles of ammonia that need to be present, or that will be produced. Theoretically, this is a theoretical number. So now that I have moles of ammonia, what else do I know about the ammonia? Well, I know its temperature and its pressure, and its pressure. So if I want to find liters, which is volume, PV equals nRT. I need to find volume. So you divide both sides by pressure. I have moles. It's right here. R is given, right? I have temperature and I have pressure. Just plug in now. So 40 moles of ammonia. The R constant was 62.4. It was given. The temperature was 27. So plus 273, would that be 300?
Yep, 300 with no decimal.
And the pressure given was 760.
Wait, was this defined liters? Or
Yep.
volume?
Volume, which is liters. Volume is measured in this chapter in liters or sometimes milliliters. So you just plug these in. Volume equals all of those numbers. So 40 times 62.4 times 300 divided by 760. Ugh. So without sig figs, the number is 985 liters. I'm probably not going to grade on sig figs on this one because this is a 1 sig fig number. So is
Yeah, I did
this.
the sig fig and
So
I got 1,000.
it's 1,000, but I will probably be lenient on the sig figs on this one. 985 would round to 1,000 to make it one digit. Because this is 1 sig fig and this is 1 sig fig, so your answer could technically only be 1 sig fig, but I'll likely accept both of these. Okay. All right, last one. It says, with the help of electricity, you can make water break apart into hydrogen and oxygen. What is the volume in liters of oxygen produced if 22 grams of water decompose at STP? Now, because I give you water and I ask you about oxygen, I'm going to have to do mole ratios because I gave you something about this guy, but I want to know about this guy. Now, the nice thing about being at STP is that 1 mole of any gas occupies 22.4 liters at STP. So you take your grams of water and you convert it to moles of water. So 22.0 grams of water. And water's molar mass is 18.02 grams per 1 mole of water. Now, I want to know about oxygen though, right? So now that I'm at moles, I say for every 2 moles of water that react, 1 mole of oxygen is produced. That gives me moles of oxygen. Now remember, there are again 2 ways to do this one. So if you want to find volume, you can use ideal gas law. I now have moles. I could put that there. R is given. Standard temperature is 273. Standard pressure is 1 atmosphere. 1 atmosphere is pressure at standard pressure, and 273 is standard temperature. So you could just plug into here using this moles, whatever this moles comes out to be. Okay? That's one way to do it. The other way is if you recognize you're at STP, you can turn moles into liters using that molar volume. 1 mole of any gas at STP occupies 22.4 liters of space. So you could just do this. 1 mole is 22.4 liters. It's kind of like a shortcut way. You only get to do this if you are at STP. If you are not at STP, this is the only way you could do it. That would be your only option. So basically, you'll never go wrong using the ideal gas law. I don't know the answer, so let me see. The answer comes out to be 13.7 liters of O2. So basically, if you were to take 22 grams of water and you were to decompose it at STP, theoretically, that's how much oxygen should be produced. That's how much you should collect in a perfect world with no errors, which is impossible. But all these calculations we're doing are theoretical values.
Mr. Murphy, how many?
The link into Canvas